There are nice relationships between the Gauss-Jordan operations and determinants, or how determinants change according to by application of Gauss-Jordan elimination steps. Like we have a multiplication of a row by a scalar, swapping rows, so interchanging row I with row j, and C adding multiples of a row to another one. So this means that a row I will change in row I plus k times a row j, where row j is another row. So these are the main ingredients for Gauss-Jordan elimination, and we will see what the impact is of such operations on the determinant of a matrix. Well, first of all, multiplication by of a row by a scalar. Here we can use linearity directly of the determinant with respect to row vectors. So now we have a matrix A and we multiply the ith row with a k. Well, linearity says we can take out this k and then we get the determinant of the original matrix. So the determinant of the new matrix, let's call the new matrix A new. So that the determinant of A new is just k times the determinant of A. So now swap. We're going to interchange row I with row j. And first of all, we will assume that these are two adjacent rows. Yeah, so j is probably I plus 1. Two adjacent rows. So what happens? If we have a pattern P and we interchange rows, then actually what happens is that we switch the pattern. Yeah, so actually what we see is on the left hand side we don't have an inversion, on the right hand side we have an inversion. Another way, if we would start off with an inversion, then we dissolve the inversion, so it creates or destroys an inversion. So swapping rows, we create a new pattern and we create or destroy an inversion. So the product of P is just the same as the product of the new pattern, because we take exactly the same elements, and the sign of this P is minus the sign of the new pattern, since we create or destroy an inversion, so the number of inversions differs by 1. So if we have two adjacent rows, we see that the determinant of the new matrix that we get by swapping rows is the determinant of A new is minus the determinant of A. So we continue with B, since we only swap two adjacent rows. But what happens if we have two rows I and j, and j is I plus some constant k? Now we can establish an interchanging I and j using a number of swaps. First we swap row I with the one underneath, I until j, so we need k operations to change I with j and then move j up to the position where row I is originally. So we need k plus k minus 1 adjacent swaps. So we know that at each such swap we get a minus sign, so in total we get, in the new matrix, we get minus 1 to the power k plus k minus 1, the determinant of A, which is an odd number. K plus k minus 1 is odd. So we know that we get a sign change of the determinant by swapping two arbitrary rows. So the effect of swapping rows is a sign change. Now suppose matrix A has two identical rows. We're going to prove here what happens, we're going to show here what happens if we add a multiple of another row to row I. First we start off with the case that we have two identical rows. So now if we would swap row I with row j, then A transforms in A new. But it's the same matrix because the rows are identical. So but a row swap means that the determinant changes sign. So actually what we see is that the determinant equals minus the determinant of the matrix A, so that the determinant should be 0. So two equal rows shows that the determinant of A is 0. So now let A new be the matrix out of A with row I changed into row I plus k times some other row j. So since we know that the determinant is linear in rows, we get that the determinant of the new matrix is simply the determinant of the old matrix. With row 1 until row n, plus k times the determinant of the matrix where in row I we write row j. So the ith row carries row j, which is the same as the jth row. So here we have the row I and j. And the jth row. And they are the same. So actually we know that since a matrix with two equal rows has determinant 0, we know that the determinant of the new matrix is just the determinant of the old matrix plus k times 0. So which equals obviously the determinant of A. So there's no effect on the determinant if you add multiples of rows to others. Well, these steps are of course ideal to determine a determinant according to the Gauss-Jordan elimination steps. So the more zeros we can create, the easier it gets to find a determinant in the end.